And the job of C will be to accept strings that are accepted by A or B, in fact an exclusive OR, but will reject strings that are accepted by both A and B. You got that? Okay. Right. So now here's the punchline. Like here's the main idea for using C. So therefore, right. So if A and B recognize the same language, okay, because they're DFAs. That's what DFAs do. So if A and B recognize the same language, can you see that C will accept nothing? Okay. Because C will only accept a string, or put it this way, C will not accept a string if that string is accepted by A and B. Right? So in other words, if A and B recognize the same language, that means, if you think about it, every string in that language is accepted by A and B. And therefore, C will reject every string in these two languages. The language recognized by A and the language recognized by B. Okay? So C will accept nothing if the LA and LB are the same. Okay? So that's the core idea. So make sure you understand that. If not, rewind. Alright. Now what is the language of C? It's it's this. And here it is in sort of symbolic logic form. Now, so what strings a language is a set, right? Just a set of strings. And so what set of strings will this DFA C recognize? So in other words, what's the language of C? Well, can you see it's this? Because remember, the language of C, it's the set of strings recognized by machine A, but not recognized by machine B. And it's this bar, like the complement. Okay. Or it's a set of strings that are recognized by machine B, but not recognized by machine A. Okay, so hence this intersection, right? So the strings in this language and the strings in that language. In other words, the strings that are not in LA. That's what the complement means. Like that sort of means does not belong to. The opposite, the not in that set. We talked about complement of sets in chapter 0, so go back and refresh. So language C is of this form. Okay. Now this expression here, it's given a name. It's just called the symmetric difference of these two sets or two languages. Remember, the language is just a set. It's a set of strings. Okay. So the symmetric difference between these two sets or two languages is this, by definition. This thing is called the symmetric difference. Now, if you want to see it in terms of a Venn, V-E-N-N, also talked about, it's a way of visualizing sets and unions and intersections of sets and so forth. Talked about that in chapter 0, so go back. So the hashed area, not here, but here. So this would correspond to that. And we're talking about the union, and this corresponds to this region here. Okay, so this is a Venn diagram representation of the symmetric difference of these two sets, LA and LB. Now LA with a bar over it, that's the complement of the set LA. Okay. Now, why is it useful? Why to do this? Well, I was saying a bit before. So this set here, or the language recognized by DFA C, that'll be the empty set. It recognizes no strings if and only if LA equals LB. So the language recognized by A is the same as the language recognized by B. Okay, so this. All right. Now, how to construct C? Well, we had. Let's see, chapter 1, I think. The so-called regular operators and that set of regular languages. They are closed under these regular operators. You can remember that. Go back to chapter 1. Refresh your memory if you're rusty. Remember closure, what closure means? You perform some operation on members of a set, one or two members of the set, and if the result that you get also belongs to the set, for all possible combinations, then that set is said to be closed. And we showed regular languages were closed under union, intersection, complement. That's all we need, isn't it? Union, intersection, and complement. Yeah, that's all we need. Okay. So the techniques, the procedures, the constructions of proving closure, we can use those tools, those construction methods, to construct C from A and B. Okay. And we're talking regular languages. And from regular languages, regular languages are recognized by DFAs. Alright, so that's a little bit vague, but you can do it as homework if you like. So go back to chapter 1, find the techniques you use to prove closure, use those techniques to construct C from A and B, these machines, A and B. Okay, so which will allow you to create a DFA that, using this kind of symmetric difference formula, which would allow you to detect strings that belong to A but don't belong to B, or belong to language B and don't belong to language A. Okay. All right. Now, and then we will use the theorem. What was it? 4.4. The proof that there's a DFA that can recognize no string, that its language is in fact just the empty set. Right? We'll then use that. We'll test it on this language, L of C, to see if it's 0, if it's the empty set. And if it is, well, then we know that these two languages are the same. Okay. In other words, the two DFAs A and B are equivalent. Okay. So a bit indirect, multi-step reasoning. But that's the idea. Alright, so we then just need to, this next session, but we need to specify give the formal description of the Turing machine that does this.